Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you're watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right.
We made it.
Hello, everybody. It's been a while.
It has been. Wait,
Yeah,
did we
2
miss,
weeks.
Did we miss a week? We did miss a week.
Yeah, last week was the ECS meeting in Seattle.
Yeah.
So for those of you who were there and stopped by the Pine Research booth, thank you. It was good seeing you. But yeah, we missed it last week.
Missed a week, and we're gonna miss next week.
And we're gonna miss what next week because next week I will be at Villanova
Yeah.
University doing an electrochemistry workshop.
I didn't even tell you until this very moment because we're live and I'm very well planned about things. But I actually will also be out next week. So
Oh, okay.
even if you like thought Villanova was really boring and you got sick of the workshop and you just decided to come back to the office and it was Friday and you're like,
Oh yeah,
let's just do the live stream anyway.
let's just do it.
I will not be
You will
here.
not.
So no.
So
We're not doing it, even if you want to. Sorry, it's not happening.
Sorry.
Yes. Not sorry, because
Sorry, not sorry.
It happens.
It just happens.
Yeah.
We try, but when
It's
we're
the
here,
summer.
we're here.
I know.
But when we're not here,
It's almost funny because like I remember in grad school, I don't know if you had this experience. I always had this experience. And the summertime was the best time to do research because there were no undergrads around.
Yes. Yeah. That was.
So if you're an undergrad, we love you, but please go away. It was just nicer. The campus was more empty.
It was quiet.
It's quieter.
Yeah.
It was a lot easier to get stuff done. It was a lot easier to get, not be interrupted, loud hallways, whatever. Although sometimes the undergrads, they'd be in the lab, and they'd help, like, for the however many ones were, were part of the group, at any moment in time. But for the most part, they got in the way and were loud, and it was just nice to not have any traffic, walking around campus. And I kind of liked it quiet. So
yeah, I liked it too. I just I'm just wondering about what is it? Like it was quiet, and it's like, yes, summer's the great, like that's when we're gonna, get lots of research done. Not perturbed by like classes or anything like that. But I always felt like, research always just happened at its own pace anyway. It was like, I still also want to enjoy the summer, and if it was nice out and stuff like that. So yeah. All right, we have a question. We do have a question in the chat from the Creeper 49YT. Yes, could you explain the difference between inner and outer sphere redox probes? Do you know the difference between ferrocene-methanol and ferricyanide in terms of how they interact with the electrode surface? Okay, so let's see. So I can answer this or talk a little bit about it actually, because I am doing a webinar shortly. I do have actually a figure that might be helpful for this. So there's two things here. Let's see. Let me get to the slide. Sorry. Okay, here we go. So, all right. Hopefully, I am sharing.
Looks like you are. I'll hide the question because it kind of obscures a little bit. Yeah.
Yeah. So there's two forms of electron transfer with the electrode surface. There's heterogeneous electron transfer and homogeneous electron transfer. So heterogeneous electron transfer is when there is a strong connection or interaction with the molecule, the redox probe in particular, with the electrode surface. So the way I think about that is there's actually like a bonding interaction. There needs to be very strong orbital overlap between the molecule and the electrode. And it's most visible and obvious when you have heterogeneous electron transfer, because if you do your CV on two different electrode surfaces, you may actually get very wildly different voltammograms, stuff like this. So if you have if it's heterogeneous electron transfer, whether you get the electron transfer on like glassy carbon or like copper or gold, you'll actually get very different looking voltammograms. So that's probably the kind of simplest and way that we know whether or not we have a heterogeneous electron transfer. Homogeneous electron transfer is when the electron transfer actually tunnels through the solvent. So we don't often talk about this, but electron transfer in electrochemistry, especially when it's homogeneous electron transfer, is electron tunneling. The electron, when it interacts with the molecule, tunnels through the solvent, and that's how the electron transfer is actually occurs. It's basically independent. The electron transfer is independent of the electrode material. And that means when you do cyclic voltammetry on, say, glassy carbon or gold, relatively what we might describe as inert electrode materials, the CV looks exactly the same. And now to the main part of your question about like ferrocenemethanol and ferricyanide, I believe people use molecules like ferrocenemethanol due to solubility. So
Is that more soluble in non-aqueous?
I believe it's more soluble in aqueous systems.
Oh, in
So like
aqueous. Oh,
ferrocene,
okay. I had it
yeah. So
backwards.
ferrocene is soluble in non-aqueous
Right.
systems. Ferrocenemethanol.
Oh, that makes sense. I guess if it's it's got the methanol.
Yeah,
So
it
it's
has the
got
methanol.
it's got
That's right. It's got
the
the
non
OH.
the polar
Yeah, it
methanol
creates
part to it. Okay, so
exactly.
it dissolves in
So
aqueous.
it's supposed to dissolve more in aqueous. Although every time
I never use ferrocenemethanol, so
yeah, I have maybe used it once, but I actually don't find it that soluble
oh,
in water
well, it's probably
because it's still
ferrocene. It's still mostly ferrocene.
it's still
right?
mostly ferrocene.
Yeah,
It's
so
just
it
a
probably
little
doesn't.
soluble.
But does it act? And I'm asking actually. I mean,
No.
I'm asking you about electrochemistry today. So yeah, no, it's
Yeah.
is it similar to ferrocene in non-aqueous, whereby you only need a little bit of it to get
Mhm.
a peak by which you can like calibrate a reference electrode or something like that? Or
Yeah.
so you don't need it. So it's like it's not very soluble, but you don't need a
Yeah.
ton of it
You don't
anyway.
need a ton of it.
Oh,
Yeah,
that
that's
works.
true. That's true.
You know, sorry, are you finished? Because the next question actually there's some dovetailing with what you just talked about.
Oh, okay. Yeah,
So
sure.
Nakib Lucky
Mhm.
said, is potential various or probably varying, I guess, with catalyst or with compound that you're trying to reduce or oxidize, like we reduced nitrate. So potential for the catalyst or for nitrate. So actually, the funny thing is, Alex kind of just talked about this in some sense with the heterogeneous versus homogeneous, right?
Okay.
So you could, one way to look at this, and to answer your
Yeah.
question in some sense is almost like, you're going to have to find out, perhaps maybe read the literature for like, what if you're doing some nitrate redox or you're doing whatever else you're doing, is that a heterogeneous or a homogeneous um process, right? Because, and correct me if I'm wrong, Alex, but basically like if what you're studying is a homogeneous electron transfer, essentially the answer to your question is that it varies with the compound and not the catalyst, because when it's homogeneous, there's electron tunneling,
Mhm.
and it doesn't almost matter what the catalyst is. Now,
Yeah, what the electrode is.
what the, I'm sorry, yeah, what the electrode is, what the catalyst is. But if it's a heterogeneous electron transfer, then it probably more strongly does relate to what the catalyst of the electrode is.
Yeah, yeah.
Does
The
that make
surface,
sense?
yeah, its ability to interact with the surface,
Yeah.
plays a bigger role,
Yeah.
generally speaking.
And then the other thing that I would say is that to a certain extent, and again, I could be a little off on this, but whether it's heterogeneous or homogeneous, or maybe you're not sure, to a certain extent, with any bit of electrochemistry, you're probably going to find practically that it always depends a little bit or a lot bit on the electrode or the catalyst itself.
Yeah.
And the reason is that, for example, if you're studying something like oxygen reduction reaction, just make up so this isn't nitrate.
Yeah.
I'm just picking one that I'm a little more familiar with, maybe, right?
Mm-hmm.
So the oxygen reduction reaction should, take place at 1.2 whatever volts
Yeah. Mm-hmm.
Versus NHE, right? Um, so you should get a reduction like wave or peak. Well, when you use something like platinum, it's it starts going pretty negative, and you get a good like oxygen reduction current and
Mm-hmm.
wave and everything. When you use glassy carbon, it might not happen until you get to like 500 millivolts or something. Like you have to go way more negative before you start seeing it. Now, does that mean that the oxygen reduction reaction is like changing its standard potential?
Mm-hmm.
No. It means that your catalyst is just not very good at doing the oxygen reduction reaction. So to your point, when you're saying like, is the potential varying? It's like, no, right? The potential of the oxygen reduction reaction is not changing. It's just that the over potential
Oh,
required
yeah.
to do it
Mm-hmm.
is greater.
Yeah.
So maybe
Yeah.
that is what you're saying, and just
Mm-hmm.
just to be clear, the wording when you say the potential is varying, it's like the over potential is greater, like because glassy carbon is a worse catalyst. It's not a great one,
Mm-hmm.
which is on purpose, right? Because you're trying to usually put a film onto it of some novel material you're trying to test. And so we wouldn't want the glassy carbon to be good at doing oxygen evolution or oxygen reduction or whatever, because we want it to be overshadowed by whatever we're coating it with.
Mm-hmm.
So that's on purpose. But that's kind of a point to answer your question, is that a lot of times the varying, right, to your question of potential is more related to the electrode, the catalyst, whatever, right? Because each material, each metal, each catalyst, right, has its own like activity, sort of not the right word in a
Mm-hmm.
scientific sense, but its
Yeah.
own how good or bad it is at
Mm-hmm.
performing certain redox processes, right? And so that
Yeah.
will affect its over potential and then the potential that you observe, basically. So
Yeah.
I hope that's clear. That's kind of the two ways that I would say to answer that. Is one is
Mm-hmm.
the heterogeneous versus homogeneous
Yeah.
electron transfer that can have some impact as to whether the electrode or the catalyst actually matters, in some sense. And then the other is just this concept of over potential. So
Yeah.
that's the comprehensive way I guess I would answer
Mm-hmm.
your question. So
Yeah. Yeah. No. And then I don't know if he
yeah, as a follow up question here,
yeah, just follow up like what it means by negative potential and positive potential.
yeah. Mm,
Great question. We're getting into potentially fundamental, like real fundamental electrochemistry,
yeah.
but um it's really so the way I think about it, it's really to a certain degree like directionality. And negative and positive potential, loosely speaking, you can think about for a negative potential, it's like the buildup of negative charge to reduce or donate an electron to something. And a positive potential would be something more akin to building up of positive charge to induce, say, an oxidation reaction. But the thing is, you can have, let's say, you can have a buildup of negative charge, but if it's relative to something with even more negative charge, then its potential might be positive with respect to that thing. So that's kind of a weird thing about like negative and positive potential. It all has to do. It's a relative quantity. I actually give a. Let me get the other slide from my.
Just pull up all the
Just pull up
slides.
all the slides. Let me actually get it because I do like to. It's like I'm just gonna give the all the Villanova
Yeah, you're
lectures
gonna
just like right now.
you're just gonna give it all away right now. It's fine.
Yeah. So
There's no point in going to Villanova at all.
yeah. So in reference electrodes, like let's say you have, let's say, the standard hydrogen electrode, and we define that at 0, and there are these two redox reactions. One's happening at a negative potential. So in this case, I have a reduction reaction, and the other reaction is an oxidation that happens at a positive potential. So you may employ something like a silver chloride reference electrode, and as we kind of go, we can measure like, oh, this thing is a positive voltage with respect to with respect to SHE versus this reaction. And similarly, it would have a lower positive voltage or potential with respect to silver chloride. And I can go, vice versa. I have a negative potential with respect to silver chloride, and then we get a less negative potential with respect to SHE. But if I have another, or what I'm going to call a magic reference electrode, I can measure a negative potential with respect to this reduction reaction. So, or with this oxidation reaction, C goes to D plus an electron. So I have a negative voltage, negative potential, but I have an oxidation process. So that's when I say like those negative potentials, positive potentials, it's all relative to something. But generally speaking, when we have negative potentials refer to like reduction reactions, positive potentials refer to oxidation reactions, but the place with which you measure it with respect to will determine whether it's positive or negative. So so hopefully that kind of provides a little bit of clarity on what do we mean by negative and positive potential. But of course, let us know if you have further clarifications or questions, things like that. Okay. This person said the best part.
Yeah.
Video. Summertime is the best time to do research. Undergrads aren't around.
Yeah. See, I guess you agree with me. I mean, it's definitely the correct opinion, I hope you're a grad student and you appreciate that as well. Also, this person says by tunnels through the solvent, do you mean the hopping mechanism? I don't. Is that another name for it? I'm not really familiar with that.
I'm not so sure.
Hopping electron transfer. I'm not. I feel like I've heard of I've heard something in my brain is like
you may have heard of it.
Feel like I've heard it, but I can't recall precisely, to be honest. Yeah.
Like tunneling is a term used in like quantum mechanics for something kind of moving past a high energy barrier. Like electrons are able to tunnel through the solvent because normally they can't tunnel through the solvent. There's like a super high energy barrier. But quantum mechanically, there is a statistical probability of the electron actually doing that. Because there's no orbitals in the position. So it can hop, or I guess, you can use the word hop, but I've always used like tunneling. That's just like the term that I've used. So if you have any questions, let's see, does it have any like further questions?
No, nothing yet at the moment, but I can't precisely answer, I guess. Because the hopping mechanism isn't something I'm really familiar with.
Yes.
As I said, it's possible that I've heard it in the past and I just can't recall what context, so I won't comment further.
I would say, so like tunneling, if you look up quantum mechanical tunneling, that is the mechanism. And if what you read on quantum mechanical tunneling fits your description of hopping mechanism, then it's probably just it might be the same thing.
It's a similar or another name in a different, like physics versus electrochemistry or whatever you want to say. Like sometimes similar phenomena have I guess different names across scientific disciplines or something like that, right? You'll have a similar kind of thing. So anyway, so like we call it like cyclic voltammetry, right?
Yeah.
But like a physicist calls it waste of timetry.
Waste of timetry.
So there's just different terms, that's just, it's fine. You just got to respect what people call stuff. Speaking of things that are waste of time, supercapacitors. Rocktick says, which test is good for supercapacitors, CV or GCD, and why more accurate results? Well, it's not necessarily a question of accuracy. Both tests can be done for supercapacitors and are done for supercapacitors. As I said, it's not necessarily even really an accuracy thing. A lot of times it's just what you're after, what you're looking for. So generally speaking, what I would kind of say here is when you're doing for supercapacitors, supercap, right? If you're doing CV, a lot of times what you're doing is you have potential down here and you have current on the y-axis. And what you're doing a lot of times is a scan rate study. So you'll have like scan rate is equal to 50 millivolts per second. Just make up some numbers and draw some representative stuff. And so you're gonna, a lot of times what you're doing is you're starting somewhere, you're scanning. It's basically, it's non-Faradaic because it's a capacitor, right? And then you'll increase the scan rate to 100 millivolts per second. I'm just shorthanding it. You hopefully understand the units the same. And basically the current increases a little bit. And then I'll just do one more. I won't do this like 15 times and bore you to tears, right? And then let's say we do 200 millivolts per second, and you can imagine it goes up more. This should probably be drawn more to scale, and hopefully you get the idea. So with the CV, again, it's not really a accuracy or not accuracy comparatively. It's more like what you're after. And so what we're looking for here is that a lot of times we're trying to measure the capacitance, right? And in this case, what we have is that like this CV sort of goes up and down over the like zero, I is equal to 0 usually. And so what we're doing is we measure like the current, which is sort of like half of the CV, if you will. We call this, the current that we're measuring, I of the supercapacitor or whatever. And I, the current, is equal to the capacitance times the scan rate, right? And so basically, if we just divide whatever current we get by a scan rate, we get a measure for capacitance. You can also make like a linear fit where you plot, I think, I versus scan rate and get capacitance. So you can do it on an individual basis. You can also plot like each I and each scan rate, and then the slope is of a lot. Like, you make a separate plot of I versus scan rate, right? And you'll get points, and then you can get the slope, right? And the slope is the capacitance. So that's like what you're measuring there. Now, GCD is just going to be a little different. It's galvanostatic charge discharge. And so in this case, what you're doing is you're applying a set current. See, the CV is what you're doing is you're sweeping the potential. It's a potentiostatic method. You're controlling the potential and you're measuring the current, and then you're getting a measure of the capacitance. Galvanostatic charge discharge, you're getting often what's called capacity, not capacitance. So in this case, on the y-axis, we flip it and we have potential here. And so we have sort of this like E upper, we usually have an upper limit. This is a similar thing for batteries, but supercapacitors are often done in a similar way. And then we have like a lower limit, right? We have a lower and an upper potential that we are working with. And then basically you can think about the x-axis as time effectively. Okay. And what we're doing is we're setting I is equal to, X amps, a certain amount of current. This is a certain amount of current. And when we do that, what we're going to observe is that the potential is going to start at the lower, potential, and it's going to rise until it hits the upper potential. Or if I should put plus or minus, because if we apply negative current, then the potential will drop until it gets to the lower potential. So you can do either, one. But what you're doing is you're basically measuring how much time it takes. And then effectively it's like an integration. So sometimes we use units like amp hours. So you can say how many amps did I apply times how many hours or minutes or seconds that it took to get from one potential to the other. And capacity, not capacitance, capacity is, sort of, I'll just say like defined by, you'd say like amps times hours. Or that's also not to be confused with capacitance. I'll write the word out because it's not coulombs as a unit is charge. So capacity is like charge. It's the amount of charge that it can handle. So these things are related, but capacitance, from this equation up here with the CV, is in like farads, right? This is capacity. So this is how much current can I apply for a certain amount of time, or how much charge can be stored, basically. You could think about it that way, because a supercapacitor is a charge storage device. So that's just a sort of a very brief, without being too much more specific, about each test and what they give you. Again, it's not a situation of which one's more accurate, but they just give you different properties and different kinds of analyses per se of the supercapacitor that you're studying, right? So I hope that kind of I don't know, clears that up
Mhm.
for you. And in some sense, I guess the takeaway here is don't maybe think you like have to pick one. Do both. They're both potentially helpful for characterizing your supercapacitor material. So you can certainly do both.
Yes. We do have a bunch of questions coming in, and one thing I'd like to let you know that if you're just like, man, why can't you guys get to my questions too? We will get to them, but if you want your questions answered as soon as possible, you should submit your questions ahead of time to our website. And on the Pine Research website, there's a little button right here. They gave us not the YouTube one. That's where you're at right now.
That's right.
But send us a message, and when you send us a message here, you can select the option YouTube live stream question submission, and these questions will get prioritized. So if you have an account on our website, right now it won't load this form, um, but when it does work, you need to submit them here, and this will be the first thing that we actually answer during the start of the live stream. So just letting you know about that. And yeah, just letting you know. So
It loaded for me.
it loaded for you? Okay.
I don't know.
What
Our
happened?
website doesn't like you.
The website just doesn't
Are you
like
not
me.
logged in or something? Are you not
I
logged in?
am logged in.
Well, it just doesn't like you.
It just
I
doesn't
don't know.
like me.
It just glitched out on you.
Yeah.
But since the website likes me and not Alex, here, this is the form when it loads.
Yeah.
I don't know why it decided to
Oh, okay.
not
All right.
like you, but
Now it loads for me.
wait, where is it? There it is. Okay.
Just
Well,
wanted
yeah, whatever. Here it is. It should load for you. And this is my number if you want to give me a call. 555555555. All right. So whatever. The point is, when the you can add your YouTube handle so we can identify you, because it's probably some set of digits and numbers and things, and you can drop files. This is the benefit we're hoping to offer too, because in this YouTube chat we do our best to answer your questions. But if you have a question that's like, hey, why does my data look weird? It's like, well, I can't look at it. It's a YouTube comment, but you can submit, just drop a image or a screenshot of something
Yeah.
and then type in your question here. So we
Yeah.
invite you to do that if you don't feel like waiting.
Yes. Yeah. Okay. So now going back to the questions in the order, and we do see all the questions that are coming in. We are getting to them in the order that they have been submitted. There is a question, an EIS question.
Oh.
For EIS, does the frequency itself from high to low partly correspond to the rate of charge transfer, i.e., at solid electrolyte interface within catalyst layer, respectively?
Charge transfer
itself from high to low partly correspond to the rate of charge transfer.
The rate of charge transfer. Does the frequency itself correspond to the rate? Not really in the way that you've asked it.
Yeah.
What I would say is that at some frequency or some range of frequencies, very likely there will be like you will be at a frequency where you are measuring the speed, so to of the frequency of the measurement is corresponding, I guess, with the rate of charge transfer, like the speed of the reaction. So in some sense, I guess the answer is yes. But it's more like just not all of the frequency necessarily. And it depends how many charge transfer processes there are. But like, let's just say you have one charge transfer process. It's more like if you just scan from high to low frequency, broadly speaking, at some point over some range of frequencies, you will probably be probing mostly that charge transfer process, because those frequencies are along the same speed, like rate, as the charge transfer process. That's when you get the semicircle, basically. Like when you get a semicircle, the frequencies along that semicircle are usually, at the speed of the process under study.
Yeah.
So I guess in some sense it's almost like it's just worded. I'm trying to.
Yeah, there's like a
So
couple. Yeah, so I know it's in this case it's like, okay, solid electrolyte interface, and then like within a catalyst layer. So there is the frequency, but there's also the potential at with which things. So if you think about it, the rate of charge transfer is a function of the potential, right? Like if you go to higher potentials for a certain reaction.
that's not true. You just do it at OCP.
What?
You
Oh,
just do it
you
at
just do it at OCP.
This meme is very
This
important.
meme is very important. Right. Yeah. If you did it at OCP, it's like, well, there is no charge transfer. So the rate is like non-existent.
It's
Or
zero
if it's a little
or whatever.
potential, then the rate is slow. So the rate of charge transfer, it's like the frequency helps you probe the rate, but the rate itself is not a it's not it's not a direct correlation, sort of say. It's like the potential determines the rate of charge transfer, as indicated that when you do EIS at open circuit potential, it's like, well, the rate is like non-existent because
Yeah.
there is no process happening, even though we know that reaction can happen, just not at OCP. Um, so so yeah, that's how I would think about it. Like, let us know if you need more clarification on that question. So
Yeah.
um,
I think that's a good point. Yeah.
yeah,
The applied potential definitely has a lot more to do with
Mhm.
what the rate is, but then measuring it has to do with what frequency you're at.
Yeah.
And so, yeah, in some sense, the spirit of your question is good. It's like
Yeah.
you're
Yeah.
actually thinking
He's
it.
thinking about it.
You're thinking about it, I think, correctly in a sense
Yeah.
that
So it partly does partly
yes,
correspond to the rate of
I guess
transfer.
that's so. I guess that's
So I guess
correct
we can say yes because
for the most part. Yeah.
partly.
Yeah, but those caveats about what
Yeah.
influences, which is the applied potential, the overpotential, that rate, and then at
Mhm.
some frequencies you're sort of probing it preferentially or whatever. So
Yeah. Absolutely.
yeah. All right.
Okay.
So Hab
G. Yeah. Hab G is asking, is it the SHE that's theoretical and to be to be built the absolute zero of electrochemistry? Oh, is the other a theoretical that's built to the absolute? Okay, so I will say this: SHE is theoretical. NHE, which is normal hydrogen electrode, is actual, like it's an actual experimental thing. SHE, that potential, because in real electrochemicals, like an NHE is when you take like a platinum wire, you have it in like 1 molar of sulfuric acid with 1 atmosphere of hydrogen gas, and it's that potential. So everything with respect to that potential. But um, oftentimes, if you were to actually set up that kind of reaction, which is good, it's good to do. NHE is great, but the SHE, but in an NHE you have anions, you have solvent molecules, you have non-idealities, and so the SHE is technically a theoretical potential. So it assumes that all those other anion effects, if you used hydrochloric acid versus sulfuric acid when developing the NHE, how those things play a role, would change. So so SHE is theoretical, but maybe not the way you thought it was, because like H2H plus 2 electrons does give you hydrogen gas. That's very real. But the actual potential from a strict definitional way is theoretical. And that has been defined as, I wouldn't call it like it, I think it's good to just say like I don't want to call it absolute zero because absolute zero has like temperature implications and
yeah,
and
it's the
stuff like that.
potential reference point.
It's
is what it is.
Yeah, it's a
So
reference point.
we wouldn't use the word absolute zero. That makes it sound like it's 0 Kelvin.
Yeah, or it's at the bottom of the list, but it's actually in like the middle
It's
of
in
the
the middle
list.
because there's positive and negative potentials with
Yeah.
respect to that. Yeah.
Yeah. So those are just little like clarifications, but like very good question. I mean, unless you're like just doing electrochemistry for as long as we have, like you wouldn't think about these kinds of like crazy abstract things about potential and stuff
Yeah.
like that. Okay. All right. So, Habji, I hope that answered your question. There's another question. There were kind of two that are related. There is a methodology to find the correct equivalent circuit for EIS fitting, and more. I think
It's the same.
kind of the same question. Like, is there a specific methodology
for the
to
Nyquist
follow
plot.
for Nyquist plot fitting
Yeah.
and stuff like that?
Yeah, sort of, but it's more like so a lot of this just comes with experience of doing it, but you're talking about a methodology for finding the correct equivalent circuit. It comes from just recognizing patterns and shapes. So it goes something, and I talk about this in one of my webinars, my impedance webinars, like the circuit fitting one. I think I kind of walk through tips and tricks about circuit fitting, and it's that webinar that is on our YouTube channel. If you want to go check it out, partly answers your questions. But you can think about it as almost like a multi-step process. So it's like, what should my circuit be? Well, first of all, whatever I have for my, if I'm looking at my Nyquist plot's the one that's probably easiest to analyze in this regard. Z real, Z imaginary. Whatever I have for the, it doesn't have to start below the x-axis or the y-axis.
You hit undo and it didn't.
I know it
destroy
did.
Yeah, that's
I
amazing.
hit it and I was concerned it was going to crash my computer. Somehow it didn't crash it. That's impressive, right? So wherever this sort of starts, right, whether it creeps below or not, it doesn't really matter. The first kind of thing we have is that this distance from the origin, from zero, basically zr, this is ohmic or uncompensated resistance, R0. So basically the first, like, well, how do I correlate with whatever circuit? You'll almost always have a leading resistor. So that's like step one. And it's on the Nyquist plot, it's the like physical distance on the x-axis where the points start at high frequency. The next things to do are to recognize patterns, right? And so you may have patterns that look like just a semicircle. You may have patterns that look like a semicircle with a tail. You may have a pattern that looks like two semicircles. You might have this kind of lagging portion here. You might have mostly semicircles. Basically, for each semicircle, the first thing you should try is adding what's called a void element. So it's a resistor and a constant phase element, CPE, or a Q. Sometimes people with the letter Q, in parallel, right? So this, just call this like R1, I guess. So for each semicircle, I'm going to put one of these things. So in here, this black one, I have one. For the red one, I have one. For the blue one, I'll have a second one over here. So I could have, for the blue circuit, I would have two of these. So this would be like CPE. I should put one over here, whatever. CPE 1, and then I have CPE 2. Yeah. So basically, it's like I'm just going to add one of these for each, for each semicircle that I have. And then basically the last thing is that if I have this kind of tail, which I'm covering mostly the things that are the most common to do that you see, this kind of tail, that means that in one of these circuits, I would replace this with what's called the Randall circuit. So instead of having it just be an R and a C, I would have it be a CPE here. And then down here, I'd have a resistor in series with either another CPE or a Warburg element. So this is the Randall circuit. So that is what replaces that. Now, there's a ton more I could say, and I won't, just for the simplicity of this answer, as well. Again, I have a whole 5-part EIS webinar series here on our YouTube channel. You can check out those if you want more thorough, analysis on everything. But basically, these are just like some of the very simple kinds of patterns to look at. And then, as you start seeing these shapes, the tricky thing will be that you'll get a Nyquist plot that looks like whatever. That's crazy. But my point is, like, is this 1, 2, 3, 4 semicircles, or is this one semicircle, right? Like, you'll get things like that where you just don't know. And unfortunately, the answer is first to do Kramer's Kronig, check if it's valid. But assuming your data is valid, there's just trial and error required here. So like if something that you're looking for instance, is like, oh, how am I supposed to know, is this, 1 to 5, RCs, like how many is it? You know what I mean? How many semicircles are really here? Well, the answer is trial and error. Like, and also, the other part of this that's the tricky thing is that it's up to you as the researcher to hopefully know something about your system, right? Because each RC or RQ, RCPE, whatever, unit in your circuit should correspond to some kind of charge transfer process, which usually means like a Faradaic, there's some charge transfer. There's some redox process occurring, right? And so if you have no Faradaic processes, you have no ferrocyanide or ferrocene methanol or ferrocene ethanol or ferrocene butanol, whatever. There's nothing in your system. Are those even real? I don't think those are real.
What?
Ferrocene butanol and ferrocene
Ferrocene
ethanol.
butanol.
I'm just being ridiculous. But my point is, if you don't have anything like Faradaic in your system that can undergo redox, well, you probably shouldn't fit like 4 semicircles because those don't correspond to anything. So there's 2 ways, about circuit fitting in some sense. One of them is just making the dots look close to the lines and your fit looks really good. And the other is getting a fit that most accurately represents the reality of what's happening on the surface of your electrode, trying to capture that reality. In my opinion, personally, I find that second thing to be more important because, there's some empirical value a lot of times in science to fitting a model to something to be able to use it as a prediction, predict behavior. But a lot of times circuit fitting is not really about that. We're actually trying to learn something about our system. We're really trying to learn something fundamental. What is the charge transfer resistance? What is the capacitance? What is the what is the double layer? What is the charge transfers? What is the uncompensated resistance? We're trying to learn something about these values, and we're trying to learn about how they change when something else changes, when the applied potential changes, when the catalyst changes, when the electrolyte changes, whatever. And so if we just have a bunch of random parameters, it's like fitting a 100th order polynomial to 100 data points. It's like it might go through all the points quite nicely, but it doesn't give you any real information. Maybe predictive information, but not really scientific information, like understanding what's happening in our system. So some of the methodology, in some sense, right, is learning about what is happening, like microscopically, like understanding the mechanism, the processes. You have to read some literature to maybe sometimes learn that. But I hope that kind of makes it clear, basically. So talk through some of those things, and then again, submit on our website if you have a specific data set and you're like, well, here's mine, I don't know how to fit it. Use our website, submit your question. You can include your data, and I might be able to. If you actually include the 5 columns of data, I could actually load it into our software and do a circuit fit with you and try to fit it. And I can do that. If you provide, if you can. I mean, sometimes I know you can't always provide me your data for one reason or another. But just wanted to throw that out there because we have our software, and I have we can do circuit fitting, and I can usually try to help with those kinds of things if you're able to submit me your data. So
yeah. Excellent. So we got 2 questions. This comes from something early. Can you share your PSF slide from electron chemistry? Unfortunately, I do not share my slides. Maybe I could, if you want, contact us, and I can at least show you, give you a PDF of the section of slides from the live stream. So use the contact us to do that. But I don't make all my slides publicly available. Unless you attend a workshop or something like that. So I always encourage you to attend a workshop. I want to do LSV for reduction. Can I give potential from positive to negative or from 0 to negative? Good question. So I would say you can, like, it might not damage or destroy anything if you start at a more positive potential or zero. But really, what I'd recommend is you determine the open circuit potential first. So the open circuit potential tells you the potential where there's no current, no reactions occurring. That can be at zero, that can be in positive potentials. It could also still be at negative potentials as well. So when you take the open circuit potential, you might find that in your system, it's like plus 100 millivolts. Well, then if you're at zero, then you're already starting to do a little bit of reduction. You want to be at least positive or slightly positive of 100 millivolts before scanning negatively when doing LSV for your reduction reaction. So it's not whether or not it's from positive to negative or zero to negative, but from open circuit potential to negative. So that's my 2 cents for you on doing LSV.
And our friend here, I think it's Wu Yishuan, followed up by saying, I asked about the scenario under electrocatalytic reaction. Does high, I'm not sure if this is a question or just a clarification, just sort of just finishing the thought. High to mid frequency, for example, to 10 hertz, probe the faster charge transfer part of the electrode. So yeah, as you scan from high to low frequency, you will scan the faster charge transfer parts or reactions like first as you go from high to low, because EIS is sort of fundamentally using frequency to probe what's happening as a function of time scale, because that's what frequency is. Frequency is the speed. It's like how it's a speed of time. It's the inverse of time. So fast frequencies are probing fast reactions, fast charge transfer processes. It doesn't have to be charge transfer processes. Resistors are like instantaneous, super fast, right? Large capacitors or diffusional processes are very slow. And charge transfer processes can be anywhere. Could be fast, could be slow. So yes, basically just to sort of reiterate, and again, maybe that's the point, and maybe you're just commenting. I'm not sure if you're asking for clarification or you're clarifying yourself. But the point is that absolutely from high to low, you're probing the fast charge transfer to the slow, charge transfer processes as your frequency drops, because the frequency is the thing that is determining which speed of process you're studying at any given time. That's like fundamentally what impedance is really great for,
Yeah. Okay. And then he says under electrocatalytic reaction. So that defines the potential
as being
with which.
So that was probably what he's also clarifying, is that you were saying that it matters what potential you're at. And so if we have applied
if we're under catalytic conditions,
exactly, then there's a charge transfer process occurring for sure. And if it's relatively fast, you're probing it at the fast frequencies, most probably.
Nice.
So yes.
Okay, good. Hopefully
very good. Yeah, feel free to give us any more questions if you need a follow-up.
We did get our buddy Chris was curious about good reference standard methods for ion exchange membrane characterization. I had to ask.
It's not 9 membrane.
Yeah, it's not 9. I asked him like, what's like 9? Is that a new classification of membrane?
Yeah,
is this gonna like change the world? It's like
9 membranes.
Just ion exchange.
Oh, that's just yeah. I'm not sure I've seen that shorthand for ion exchange.
Yeah.
Yeah. Anyway, so
I was gonna share the advanced Lugan low membrane.
Oh yeah, that's what I
thought
that
was gonna.
That is what I was gonna share too. I have.
Oh yeah, go ahead.
So I don't have a reference. I know that my group in grad school, for instance, we did not this exact cell, but we used something similar. I think one of my colleagues in grad school made something similar to this, like probably, I don't know, just with whatever that we had in the lab. But this kind of thing here is the sort of fundamental, if you will, kind of way that this can be done. There are more pictures here. Just trying to. So you can see that basically there's these 2 glass cells, right? And then there's the Lugan tubes that go into the middle and point towards the membrane. Okay. And the 4-point impedance measurement to get conductivity is basically like a benchmark kind of test that people do on ion exchange membranes for the most part to calculate their conductivity. Now, there's a lot of caveats that go with that because something like Nafion, for instance, you can measure Nafion sort of plain by itself, whatever. A lot of times when a Nafion is used in a fuel cell or an electrolyzer, it's soaked in sulfuric acid, for instance, overnight to load it up with ions, and its conductivity may change. It might degrade slightly. It might behave a little differently. There's things like that, and so you can measure the system. You can measure the membrane under different, systems or situations or whatever. But for the most part, that's a 4-point measurement of some kind, a Lugan measurement, whatever, to get a conductivity. Usually, I guess like Siemens centimeters or Siemens per centimeter, whatever the correct unit is. It's conductance or conductivity, something like that. That's kind of the benchmark measurement that you can do with a membrane, basically, that I'm aware of.
Yeah.
Other than that, really, the method of interrogation of an ion exchange membrane is using it in a system, which is like a very annoying answer. It's like, well, yeah, I'm trying to use it in a system, but before I do that, I want to know how good it is. And it's like, I know, but ultimately, like the way to test if it works is to build a thing and test it. Now that usually involves, using like state-of-the-art standard stuff, right? Because it's like if you're testing electrolyte or membrane, people use like symmetrical cells, or they do like platinum on both sides, or they use like the standard for anode cathode or whatever, to take those out of the equation effectively, because that they behave a certain way, they behave ideally, or that it's the best, whatever. You're not going to like test a novel catalyst at the same time as you're testing a novel membrane, because then if it doesn't behave well, which one is the reason? So I guess that's the bad news, right? In some sense, is that other than a membrane conductivity measurement, it's like the answer is to make a full system and test it, and just see how its performance is. So that's kind of it's kind of where we're at with ion exchange membranes. And electrolytes too, for that matter. Electrolytes kind of fall in that category. You can do some physical characterization tests on you get like rheological properties. You can get all kinds of different stuff, but ultimately you have to cobble together a battery or a cell or whatever with your special material and see if it's good or bad.
Yeah. Well, that's good. That's good. All right. So HopG said, will you have your Rutgers workshop this summer? It's a great question. So far, we are still planning on having that. If you go to our website and then click on workshops, which is in the upper right-hand corner, Rutgers is coming up. And we're slated to have it basically the end of July are the dates. And if you click on view details, if you click on register/apply, it'll take you to the electrocatalysis workshop, which is on Kate Waldy's website. So we have some, I usually try to provide information about what the schedule is and things like that, but the registration will be on Kate's website. So it is slated. I need to touch base with her. Usually I don't have to do very much. She takes care of mostly everything. I'm just like, all right, do you need anything? Do you have people signed up and registered? It's like, yep, it's good to go. So I just show up with things like, yeah, that's it. Just have your presentation. It just happens.
It happens of its own accord.
There's no like hand holding. There's no like, troubleshooting a certain thing. It's like, no, everything is just like ready to go.
Everything works.
Show up and bring some things.
That's the best kind of
so
workshop.
Yeah, Jay, it'd be great if you could sign up and attend. It'd be great to meet you in real life, and you'd learn a lot. You'd also learn like a ton of stuff as well. It's a very good workshop. Well, while we wait, there is a question that was asked earlier by a guy on LinkedIn, and this question from Sonu was about how do you calibrate a reference electrode. Fundamentally, he was doing some nitrate reduction, or actually ammonia reduction, ammonium reduction things, and wanted to know about how do you know that your reference electrode potential is correct? How do you calibrate your reference electrode? So I'm going to talk just a little bit about it briefly. He asked me to talk a little bit about it, um, and so with reference electrodes, what I did as a graduate student in terms of calibrating, one of the easiest things that you can do is when you purchase multiple reference electrodes, or just don't just purchase one reference electrode, always purchase multiple reference electrodes, and then keep a reference electrode as like a quote unused master reference electrode, because one of the important things in how reference electrodes work is let me see if I can do this. So if I do this, yep, okay, good. I should be able to copy and paste that. One of the things that happens, and say this is in some kind of you have these two electrodes in some kind of solution, right? So ideally you have the same reference electrode. And if one is like your test reference electrode, this is the one that's been used in your electrochemistry experiments. And this one we're going to call it like the unused reference electrode. So it's just kind of in its own container, in its own electrolyte. The inner fill solution and outer fill solution are the same. If you hook these up to a voltmeter, some kind of voltage source to measure the voltage, ideally, you should measure approximately 0 volts. That looks like OU, but it's a let's make it a more clear V. 0 volts, approximately 0 volts, because two reference electrodes that are exactly the same should have about the same. Should have the same voltage. So the voltage difference between these two should be 0. Now, oftentimes you'll actually find that you might get this somewhere along the lines of plus or minus, I'm going to say 5 millivolts. And maybe that's about the limit. Maybe you can go a little bit more. But ideally, a reference electrode potential, if you're looking at potential versus time, it should be relatively flat. It shouldn't go up, it shouldn't go down. It should be flat. It should be just very little variation. And make sure you look at the y-axis, because sometimes potentiostats will like zoom in if there's no like big changes. And so you may actually see something that looks like this, but it's like, oh, this is like fractions of microvolts or something like that. So it looks crazy, but it's actually not a crazy result. So you want to make sure the reference electrode is stable. And this is a great way of making sure that your reference electrode, especially your test reference electrode in your system, is working. Now, in terms of calibrating, actually, how do you know whether your unused or your test reference electrodes are even good in the first place? And for that, this could be off and this could also be off, right? And you wouldn't know that. So what I did, at least when I was a graduate student, is I would actually use I actually built a kind of like standard hydrogen electrode. I had a tank of hydrogen gas, so just a valve, and this is H2. This is H2 gas. I would bubble H2 gas into a cell. So I have hydrogen, H2 gas. This was in 1 molar sulfuric acid, so forth. And then I would have a platinum wire. And actually, let me make this a little bit wider, so it's at least easier to see. So then I have a platinum wire in my solution. Actually, I would just take a counter electrode, platinum wire. And then I would relatively quickly put my reference electrode. Maybe it was silver chloride. So I'd put my silver chloride reference electrode in here. This would be AgAgCl. And I do the same thing. And then I would measure the potential between these two. And in this case, I should get the literature value. that was how I knew for sure that my reference electrodes were, quote, calibrated. And luckily enough, when I did this, I actually got something like about, 1.97, it's 1.97
197.
volts.
We mean 197 millivolts.
Or is it 1.9, is it 197 or is it 0.197?
Yeah, 190, like
100, yeah, 197
millivolts. Yeah, it's like
right.
almost 200 or whatever.
Yeah, almost 200.
Depends on the concentration
Correct.
of Cl, whatever, something like that.
Thank you. Yes. Yeah, so I get 197 volts when I looked at the difference. And if I got a negative, I just had to switch the electrode leads. But if I got this value or close enough, like, yeah, this could be 8, this could be 9, or maybe it's 6 or 5. If it was this value, I knew that my reference electrode was correct because it matched the literature value. So in this case, I had to take 2 dissimilar reference electrodes and then take the open circuit potential between them and then make sure that they match the literature value of what that voltage or potential should be. So that's how I knew. And then once I knew that, then I knew that my, quote, system was calibrated. If this was off significantly, it's like, well, I can't do very much with sulfuric acid and hydrogen gas and platinum. Maybe I could do some stuff with platinum, but I was pretty sure this was accurate. The silver chloride was the one that I thought had the higher likelihood of giving me a problem. So that's what I would do when it comes to calibrating a reference electrode. So yeah.
Yeah, I found that the hydrogen bubbling thing can be really a finicky kind of a thing. But over short periods of time for that kind of calibration, you can get results. But I find that there were always people who wanted the like NHE or SHE, like you can buy them, and sometimes they come with like a cartridge of hydrogen that's constantly bubbling, and then it runs out of it. It's like, as a reference electrode, it's ideal because it's 0, and so you sort of want that. But also, the trouble with it is that like it's finicky if the hydrogen runs out or stuff like that, and it's always just like it was always a pain in the for me to have to use those ones or whatever. So I never liked having to use the actual like hydrogen on platinum electrode. Is always a pain in the neck. I guess.
Yeah.
That's just my opinion.
But you could also you could buy a chamomile electrode and then buy a silver chloride, and then if you didn't want to use hydrogen electrode, that's fine.
Saddam has a question that says, are there any conference related to electrocatalysis for internationals? I assume you mean just like outside of the US, if there are conferences. Absolutely. In fact, a good reference for you is the ISE, the International Society of Electrochemistry. So this is the next major annual meeting for the ISE. So International Society of Electrochemistry here, their next meeting is in Sydney, Australia. So I don't know where you're located, but if you said international, I just assume you mean not the USA or maybe not North America or something. So if you're in Europe or Asia or Australia or that is that Oceania, whatever that we call that part of the world, I guess. There are certainly conferences around. The ISE has an annual conference every year. It's usually quite good and successful and relatively well attended. Depends on the location, I suppose, how easy. Australia is pretty far, to be fair, for some people, but it will be there this September. The ISE also has like other information about other meetings. Sometimes they say sponsored meetings. So I guess they're involved in these, but they're run by other folks, right? So right now it's June 2026, so we can't go back too far in time. They're no longer available. But you can see there's just a whole bunch of these. This one's in Bari, Italy, in Nancy, France, and I'm not going to pronounce that, Netherlands, Milazzo, Italy, Poland, Cameroon, Czech Republic, Bulgaria, France. Most of them are European. The ISE is pretty sort of heavily European, I suppose. But they do have conferences like this one. I guess this was one in Cameroon. I guess I wasn't even really aware of that one. But and then Gdansk, Poland, Italy, Germany, Australia, Brazil. So there's a lot of these kinds of meetings, and they also have. This is just sort of their list of meetings. So the ISE itself typically has the annual meeting every year. So as I said, the one this year it's usually in September, and it's in Australia. Next year it's in Glasgow in the UK. They haven't announced the next one. In the past, it was in Germany, Montreal. It was in France. It was in Italy one year. I can't remember. It was in the USA one year. So they move it around, and so there's always different locations there. So it's just obviously I don't know where of course you're located, but some countries may be easier for you to obviously get to than others. But the ISE is a good resource for you to see some of these meetings. The Electrochemical Society itself too, the ECS, it's sort of more of an American focus, or North America, I guess, usually USA and Canada, although they do have meetings in like in Gutenberg, that's Sweden. So they've had that one.
The next ECS meeting?
Is that, yeah.
Well, the next ECS is in Calgary,
right,
Canada.
But what I'm saying is they have some
time.
international ones.
Yeah.
Like there's the one in Sweden.
Yeah.
And then was there another one in another international location maybe?
There will be one. Next year, there's like none besides Calgary, which will be for the 250th.
Yeah.
That's this year. Next year, I think there's like none. It's like Washington and Detroit.
Yeah, so they're in the US. So
yeah,
they're mostly in the USA, but they also have information, the Electrochemical Society, ECS, Electrochem. You can check out these organizations. They host a lot of meetings. They're very good organizations. Reputable conferences, and they're well attended, and they're pretty common in the electrochemistry community for electrocatalysis. And you'll find a lot of people and people in communities working on those kinds of things at these conferences. So it's very good for international students. Again, depending on where you're located and how far you're wishing to travel, some of those could be good options. Also, Elijah says that, and I just checked, he's correct. The Rutgers workshop is full. So
well,
you can join the wait list.
I had no idea. I was just like, all right, it's another thing I don't have to worry about.
I know. It's like this. It's not on us. It's on. It's on Kate.
Kate knows all these things. So I'm like, do I have to worry about like trying to promote the workshops? Like, nope. Turns out it's already full, and there's a wait list. So still, I would say still try to apply. Because if you're like, it's like if you're on the wait list and you didn't get in, there's a very good chance next year you'll have a higher chance of being accepted because you did try to apply last year and stuff like that. So there is value in being on the wait list.
Yeah. And also just the more, it's hard especially with maybe if this one, if Kate is kind of running things mostly herself. She might be making the shots or whatever. But all I want to say is, with most of these workshops, it's like the more people who sign up, the more people who are on a wait list, the more people who are interested, the more it suggests to whether it's us, planning, right? Or whichever professors at various universities that we might need another session, or we might need a bigger room, or whatever, right? So, it's like we've had this conversation in the past, like you and me, but and it's like it's not like as we'd say in English, it's called delusions of grandeur. Like I'm gonna take over the world with this, with workshops or whatever. But you could think on a very small scale, speaking of, conferences, right? What is a conference if not a workshop that's exploded to thousands of people instead of 20 people? It's the same thing. It's people sharing research, learning about stuff. I mean, it's a little different. There's a little bit different format.
We're actually like running them through like how to like in hands-on training.
Well, they're different. So other than the fact that they're different, they're exactly the same. Other than that, but just a collection of people, in a discipline,
networking,
whether we're presenting or you're presenting, there's networking, there's education, there's community, these are all really good things, obviously. So, the more interest there is, the more these can grow maybe, and
absolutely
become the next, Rutgers electrochemistry conference. So
that's right. That's right.
I'm sure Kate will be pleased that next year, instead of 24 students, she's hosting 2,400.
Well,
just find a room big enough, no big deal.
Just find another room
and find enough like lodging, dormitory or whatever. Try to house everybody.
Stuff.
It's quite the logistical nightmare. Cricket Scientific is here.
Hey,
How's it going?
How's it going? Good to hear from you. As always.
We are doing just the wellest.
Yeah.
I hope you are doing well also.
Yeah.
369 Omniverse says you made a mistake in a coin cell during running CV 1.6 volts, 10 millivolt per second. After the OCP, the counter electrode and the working reference connected to the cathode only. So basically, you had a short circuit. It seems you said short circuit
between counter and reference or working.
Yeah, basically, just you shorted. It sounds like you shorted the battery. Will it hurt the pine potentiostat? No.
Probably not.
No, it's not going to hurt your potentiostat at all.
Yeah.
It's going to hurt you and your battery, very possibly. The potentiostat's going to be fine unless the battery explodes next to the potentiostat.
Yeah.
And the explosion destroys the potentiostat. No, it's probably not going to explode. I'm being over dramatic. But no, the potentiostat is constructed in a way that it can handle rapid or high potential or current passage. If there's a short circuit, very probably what that means for the potentiostat is that the voltage goes immediately to 0 and the resistance goes to 0, because in a short or close to 0.
Yeah.
Because what it means is you're basically directly connecting electrically the anode and the cathode through the potentiostat by connecting the wires. You're providing a pathway for current to flow between the anode and the cathode for them to charge each other or discharge, or probably discharge really. That doesn't involve the transport of ions through the electrolyte the way that you would normally do it through a resistor that is the potentiostat by measuring things carefully. You provided a direct wire path for electrons to go, and they are going to go fast. Okay. Now, that being said, if that short circuit is through the potentiostat, only the amount of current that the potentiostat can do max can go. So we have a bunch of different potentiostat models. It depends on which one you're using. It could be an amp, it could be 100 milliamps, it could be 1 milliamp. Depends which potentiostat you're using. But let's say you were using the one of our potentiostats that can do like an amp of current, then it's very possible that an amp of current was flowing between the anode and the cathode. And that's a lot. For a coin cell, that's a catastrophe. The coin cell could be totally damaged. You could have a thermal runaway, could ooze or leak fluid, it could catch fire. These are things that can happen during a short circuit event. It's very dangerous, especially if you're doing a coin cell, because when we test coin cells, it's not a commercial device. There's usually no safety features built in, because we built them ourselves and we're testing stuff. Commercial batteries tend to have safety features like vents, positive temperature coefficients, current interrupt devices. There's a lot of safety features where when something goes wrong, like a short circuit, the battery just becomes null and dead, which is safer than it exploding. So please be careful. Don't worry so much about your potentiostat. Please take care of yourself and be safe. Because this is something that can be very, very dangerous with batteries, short circuiting, right? But the potentiostat is going to be just fine. Yeah, almost for sure.
Yeah. They're surprisingly robust considering what people do to them.
Yes, yes, they are.
And then of course, it wouldn't be a good live stream if you didn't have a chance to talk about.
It's my fault. It's my fault for picking it. Right?
No, this is your cross to bear.
It is.
Right?
Yeah. Someone asked Alex about a potential window. Make him explain the potential window.
Yeah.
That's his cross to bear. So this meme, I made it. So first of all, this guy, this like old looking, I think he's like a Colombian or a Mexican guy. He's part of these commercials for this beer called Dos Equis. So if you're not familiar with this meme, hopefully you probably are if you're like an internet savvy person, but just for those who aren't, I explain it very briefly. But it's like, it's from these beer commercials that I think they're probably old at this point. But it was like they were just a joke. They were a comedy, a funny thing where they're like, he's the most interesting man in the world. He hikes mountains and skydives and does all these crazy things. Yeah. And then the end of the commercial is him sipping the beer, the Dos Equis beer or whatever. And he's like, I don't always drink beer, but when I do, I prefer Dos Equis.
Yeah.
So it's like, it's just this, so then the meme is, I don't always whatever, but when I do, blank. So that's the form of the meme. And now that I've broken every law
down,
I've broken every law of the internet, which is explaining a joke or a meme. You're not supposed to do that, but I did anyway because it's for education.
Yeah, this
don't excommunicate me from the internet. I know how to internet.
Yeah.
Okay, so this meme, it's born out of the fact that I get this question like a lot, and it just annoys me. I hate it, and I try to be kind, but I'm not a nice person, and so I'm hiding it. I'm trying to hide it. People will often ask, what potential should I do impedance at? You could get the video. I made a short about this.
Yeah.
Right? I made a short about this, and my first take was so mad
that
Alex was like, "Hey, you should redo this and not be so mad." And I was like, "Oh, you're probably right. Like, this is a video that's going to live on our channel, and it's supposed to be helpful. It's not supposed to be me like yelling at you through the screen, you know." So I'm working on my anger issues.
There's the link to the to the video,
I'll get there.
Short.
The point is, I'll try to be relatively quick, but basically people fundamentally think about impedance differently than they think about every other electrochemical experiment. And I understand why, because it's weird and it's hard and the analysis is different, and it's electrochemistry, but you don't get current, voltage, and potential, current and potential and time. You get real and imaginary impedance and phase angle and frequency and magnitude of impedance. And then you fit circuits and you do all kinds of weird stuff. And it's like, what is happening here? Is this electrochemistry? Whereas when you do CV or chronoamperometry or pulse techniques or something, you put in the potential limits and the time and the scan rate. It's like, feels more normal. It annoys me because I just don't think people should turn off the part of their brain that analyzes electrochemistry when they're doing impedance. See, I'm getting angry again.
You're getting angry again.
Because if you're going to study a redox reaction, right, and you want to do CV, and that redox reaction takes place, now I'm answering the potential window question.
Yeah.
And the redox reaction happens at like 200 millivolts. And you think, and I asked you, what are you going to do for CV to study this reaction that occurs at 200? Well, you're going to start at 0. You're going to scan, to 400 or 500. So you go through 200, you see the peak, and you're going to scan backwards, back to 0 or minus 100 or whatever. So you scan around the potential where the thing that you're studying happens. And then if I said, okay, well, I want you to generate product so you can like analyze it with a GCMS or whatever. And it's an oxidation reaction that happens at 200 millivolts. And I say, do chronoamperometry. And get, some current. Well, you're going to pick like 300 millivolts because it's like higher than the potential of the thing. It's going to generate some product. Maybe you do 250, maybe you do 350. It's whatever. You're going to pick some potential there. And then for some reason, when I say, all right, let's study that thing that happens at 200 millivolts with impedance, suddenly you think to yourself, what potential am I supposed to do? It's like, it's the same answer. It's the same answer. What are you studying? 200 millivolt thing? Well, should I just do OCP? Well, what's OCP? OCP is like 0. Well, then why would you pick 0? What's happening at 0? Nothing. So why would you pick 0? Because when you do that, your results are pointless. Like, you're just studying the like background processes or the double layer or whatever. So this is my cross to bear, and the thing that drives me nuts. It's like, just take a step back and think about impedance the same way you think about chronoamperometry or anything. It's just an electrochemical experiment. Over potential and driving force and the kinetics and the things, they're still working the same way based on what potential you pick. So don't just pick OCP and think you're going to be studying a reaction. Pick a potential that matters. So that's the meme. There you go. All right. I don't think I was that angry. It wasn't too bad.
No. That was much more
a little more measured. As time goes on, I get older and more tired, and it's fine.
It is and then I actually pointed this out to Neil earlier about like it's like a lot of people ask this question related to the meme, but there is a time when you do want to do EIS at open circuit potential.
There is.
And it's if you're doing corrosion.
Yeah.
Right? Because moving a little bit away from OCP can do a lot of stuff.
You really need to be only at OCP.
You really need to be only at OCP.
So to my own detriment, It's not pointless if you're doing corrosion. In fact, it's very necessary.
But here's the thing: all the corrosion people, when they see this, they're like, "Oh my god, am I doing something wrong?"
I know.
But all the people who are actually like
doing it
right,
I know.
like
the one group of people, the one group of like research, right, corrosion folks, are the ones that see this and are like, I'm doing it wrong. And it's like, well, you're the only ones that are doing it right. by just only doing OCP and assuming that's, you know, where you should be.
And all the people doing it wrong are like, I don't know.
It's fine.
It's fine. I'm like, oh, they don't recognize their own ways.
Yeah. I don't know. Impedance, you know, I really should have so much more like empathy and understanding, because I remember being in graduate school and being confused by impedance. And that's why I do a webinar, you know, and I talk about it on this live stream all the time. And I really do genuinely care to help people. And I like to try to, you know, give advice and show people how to do circuit fitting and do the analysis and all that stuff. I have a heart for that, like for real.
Yeah.
But just this one specific aspect of it in question, like it just eats at me and I hate it. And I have a hard time. Like all the rest of it, if you're asking me like what, you know, someone asked earlier, like, how do I figure out what the circuit model should be? Yeah. And I'm happy to talk. Yeah, well, here, this is semicircles. These are like, this is what this means.
Nobody pushed their buttons. But speaking of pushing your buttons, let's also talk about all the other things that put like chi-square. We don't talk about chi-squared
and Lugan capillaries.
Lugan capillaries.
And what about exchange current density?
Exchange current density or inductive loops,
yeah.
which I'm getting a little bit better at, I think.
Yeah, but nobody asks about those anymore. You're like off the hook. Nobody asks about inductive loops anymore.
There's still
someone
there's still
ask
some
about
time.
Inductive loops. I know we have time to talk about inductive loops and all the things that make Alex mad.
See,
I'm
Alex better at that.
Alex seems nicer than me, which is true, but also there are things that get him angry, and it's fun. so it's fun. It's fun to get you mad too, because I just can't be the only like ornery guy here. You know what I mean? The only one just like raging at the world, and then Elijah says I do EIS at OCP for corrosion. But you are correct.
You are
Elijah.
correct in doing that.
You are in the classification of people who are correct and should not be yelled at. Yeah. Even though I'm yelling at everyone.
But if you're doing, you know, ferrocenium or some electrocatalysis process,
your OCP,
and you're at OCP and you're doing EIS.
Unless you're just trying to get the uncompensated resistance, it doesn't mean anything.
Yeah.
It's pointless. It's just capacitance and uncompensated resistance. And if that's what you're into, well, good for you. Okay.
Elijah knows.
Yes.
You don't even need to go to these workshops. You already know all this stuff.
Yeah.
Like,
you don't have to come to the workshop and listen to someone yell at you about things that you're not doing wrong.
Yeah.
You know? Sai says, thank you for organizing this live event. Yeah, we do this every week. If you're new, we appreciate it. I'm not sure if you have joined us or not, but we do this. We try to do
it every week.
We weren't here last week, and we're not here next week. So sometimes we have weeks off because travel and events.
Especially in the summer.
Summertime it tends to be a busy travel one. There'll be a few weeks off over the next couple months for sure. Anyway, I just joined in. I'm actively looking for full-time opportunities. Can you please share your knowledge about how the market is and what are hiring managers looking for in a candidate? This is a really good question.
This is a good question.
So to be honest, I was just gonna make a joke about like, well, the last 3 interviews I just had, and it's like, well, don't tell my boss I'm looking for a job. No. I mean, honestly, I work here. It's been a little while since I've had an interview for a job, to be perfectly honest. So to a certain extent, I am not 100% sure, right? I can't be certain. What I can tell you about the market is actually somewhat interesting, and some of this is recent. I do have some insight as far as, well, I guess I would say what like, you know, we're a company, we make electrochemistry research products, and so I kind of know what customers are like looking to buy and based on what they're studying, right? Whether that is exactly what the market and companies would be hiring for is not necessary. There might not, you know, what academia, for instance, like we have customers in industry around the world, but a large amount of our customer base are academic, right? Research laboratories and things like that. So all that is to say, if you're looking for a job or, you know, position somewhere in industry, what's happening in academia may not exactly be the same. So take that for what it's worth. Also with the fact that I don't interview a lot, you know, I have this position I'm pretty happy with. So anyway, but all that being said, what appears to me to be the case is that like electrolysis, water electrolysis, I don't know if that's like water splitting, fuel cells, electrolyzers, those are growing in popularity a lot. For exactly what purpose, I'm not really sure. I'll be honest. But there is a lot of like my company became famous for making, Pine generally became famous like 650 years ago, for making rotators and rotating disc and rotating ring disc electrodes, because back then ish time frame, people were starting to study hydrodynamic flow on disc electrodes. When you spin an electrode, what happens? Levitch, Kateki-Levitch, these were developed in the 1960s ish, 70s timeframe. And that's what my company became famous for. We were like, the gold standard of that kind of process. And one of the main applications of the rotating electrodes, rotating disc and ring disc electrodes, is for fuel cells and electrolyzers, platinum oxygen reduction reaction, hydrogen evolution, hydrogen evolution reaction. These kinds of things have been kind of studied and researched with this a lot. And so what I can tell you again is that based on my company and what customers really are looking for, is that for whether it's fuel cells or electrolyzers specifically, I'm not 100% sure, to be honest. And the reason is because batteries, that's the other part of this, battery market is just huge, right? I mean, electric cars are growing. There's some companies pulling back for like financial and marketing reasons, but like batteries aren't going anywhere. Electric cars are here to stay. There's obviously a tremendous amount of companies all around the world making electric cars and phones and laptops and everything. So batteries are a huge industry that's not going anywhere. Development of batteries for electrochemistry is going to be something where you can probably find positions, depending on which country you're in or what have you. But for whatever reason, electrolyzers or fuel cells in that kind of water aqueous, world seems to be making a comeback. If maybe it never went anywhere, but at the very least, I'm seeing a lot of interest in that area of electrochemistry lately. So I don't know if you want to talk about the last thing about like what candidate,
like what
I just wanted to comment on the market for what I'm seeing, recently, I guess. But
yeah, no, I agree. I mean, I would also say there's batteries are very big, but also even like I hear a lot about electrowinning, and this kind of engineering things where like it's like, oh, we can use electrochemistry to pull metals,
pull metals out of rocks.
Yeah, pull metals out of rocks.
Like you use electrodeposition of small amounts of ions to get electrowinning
to get stuff. So, but in terms of like candidates, I'll also tell you this: I haven't tried to hire anybody before.
Yeah.
And so it also depends on the nature of the position that you're looking for. Like I'm assuming you're looking for like a research position, but Neil and I, like, we do sales, so there are a lot of like soft skills that are very important, just like your ability to communicate. I don't want to say like compassion or something like that, but how you interact with people is actually kind of hard to train or like into or out of. It can be trained, but it's much easier to learn like a hard skill. Like it's much easier to like, dare I say it, learn electrochemistry than it can be to like, teach someone to open the door when, when you have someone, say your please and thank yous and stuff like that. But yeah, how personal you are. I will say that I think hiring managers, every situation is a little different depending on the company. If you're looking to work at a very large company, you'll have the opportunities to grow and be promoted, but you'll also deal with a lot of like bureaucracy, and they'll kind of like put you into a cube of like, you just do this thing that we hired you for.
Yeah.
And that's it. You won't have the opportunity to like wear many hats. And so if you have a breadth, I would say, of experiences, and each one of those things is something that is good and unique in and of itself, it's like some companies, it's like, I just need you to like, wake up in the morning to make the donuts kind of thing. Like, I don't need you to do
I'll-
do something.
I'll
like,
wake up in the morning and eat the donuts.
Yeah, wake up in the morning. Eat the
I don't want
donuts.
to make them. I
You
just
know,
want to
make-
eat them.
Kind of want to make donuts now.
Yeah.
Now I'm actually curious. Like, how do we make donuts?
You gotta get like a bath of oil.
Oh, really?
I've seen it on a lot of these cooking shows. Like
Oh,
I
yeah.
watch a lot of cooking shows.
Yeah.
I love cooking shows. Like
Mhm.
and we're getting
We're getting
derailed,
way
but I don't
too off
care.
it. Sorry.
It's hard. It's really hard because you have to have like really hot oil.
Mhm.
But like, you know, if it's too hot, as soon as something is, it can explode, right? So you have to regulate the temperature of the
Yeah.
oil, and then it's like once you get the dough,
Mhm.
it literally like floats in the oil,
Yeah.
and it's like it'll be like
It's cooking.
it's underdone, just right, overcooked.
Oh,
Like it gets kind of brown, and you have to flip it like right away.
that sounds
Right,
like
or it's-
microwaving butter.
Yeah. Oh, every time you microwave butter, it goes from like it's still frozen solid
Yeah.
to separated and throw it away.
Yeah.
and
Yeah.
within
But
a
now
two
I'm a
s-
puddle.
Within a 2-second, you have to stare at the microwave. You can't walk away.
Yeah.
Yes. Anyway.
Yeah. So that's to say it can be hard to find a job. No, I'm just joking. So it might be hard to find. Another thing I will mention, I wanted to mention this. I really honestly don't know if this is good advice or not, but I think that under your skills. So first off, when you're applying to jobs, you will want to use keywords in your keywords within the position that someone will be looking for that show up in your resume or on your LinkedIn. And I actually think maybe this doesn't apply as much for us, but it's like you may want to start developing certain AI skills. It's like I think a lot of people are learning about AI and figuring out AI stuff and where does AI exist in our world and our life. And I almost feel like it's the computer and it's like instead of using a typewriter, you better learn how to use a computer, or at least. So I'm not saying go out and build, a million apps and start vibe coding, but it's like if you are using even simple tools like ChatGPT or certain AI things to enhance your workflow, to improve your output or something like that. I think that hiring managers will like that. I was actually talking to someone because I'm like, I have no idea like what sales experience I have. It's like I use a tool called SciLeads, and I never even thought of SciLeads like as being like a skill. It's like, oh, if you know how to use this software or this tool, if you're applying for jobs in a certain space, it's good to have Photoshop skills, or for us, it's like YouTube skills or something. And those things can actually be important for the job that you're looking for. So I do think, I only mentioned AI because it's becoming more prevalent, and people may be asking like, oh, how do you, because you'll probably do some data management or something like that. And it's like, if you know a little bit about using AI to enhance the workflow or something like that, that might be useful, or Python or some coding stuff. It just seems to be showing up more and more. Don't know if that's a hard, like, yes, no, you have to do this or not, but it depends on what you want to do.
Yeah. I think with AI and a lot of industries, there's a lot of people who have reason to be, let's just say, concerned about their future, because AI is in some cases able to, or maybe will in the future, whatever you want to say. So some people may be able to, will be replaced, or their jobs will be cut down because AI can do a lot of tasks. It's a sad thing, to be honest. I'm not a big fan of it for that reason. But I think honestly, the most likely end game is that it's just going to become a tool. As a general course, I take a less sort of overly pessimistic view lately about it. Just based on some things I've read and seen recently. I was a little more pessimistic about it before, but now I'm thinking, from what I see, I won't get into it more, but all I can say is I agree with you. And the reason, not just because it's prevalent now to have some knowledge at the very least, or like exposure to using like tools like ChatGPT or whatever, but because I do think probably for a lot of jobs, even if it isn't something that is like can do your job, or will be a major part of your job. It will probably, for a lot of people in a lot of industries, become a tool that employers will be like, well, we're still hiring you for this position. We need you to do a job, but
Mhm.
I want you to be able to use AI because it will enhance your ability to do your job. It's not going to take your job, but it will make you more
Yeah.
efficient, and we will want to hire you if you know how to, use it for these kinds of purposes. So to have some chops, so to speak, spend some time, like, um, trying to go through a spreadsheet, or trying to crank through some data, or write, if you're writing code, or that's one of the things AI is really good at, obviously,
Yeah.
is writing code. So if you're writing code, you can use it to help you come up with lines quicker. You can definitely write algorithms faster. If you're asking it about different um, summaries of information on the internet or whatever, it can do some of that. You have to be careful because it can be wrong.
Yeah.
So but anyway, all that is to say, I kind of agree with you, but I also think that it's like very likely to just sort of become a tool that we, whatever level of maturity that it sort of ends at, or whatever. There's sort of a craze right now with AI, and all this
Mhm.
is an insane amount of money being put into it, and all these different companies and stuff. And it's like, to a certain extent, I just think that this can't last. Like, what
Oh yeah.
the insane hysteria around it
Mhm.
in general is just not sustainable. But it's not going to go away. It's like the internet. Like, the internet was like that in the
Yeah.
early, whatever, like mid 90s or whatever. Like, when the internet and there was the .com boom and all this crazy stuff, and then, like,
Yeah.
the Enron and WorldCom, these companies that were scamming people, and it was like people. Then it all collapsed. The stocks collapsed or whatever, and people were like, "Oh, the internet's going away." It's like, no, the internet didn't go away. It's just
Yeah. It's just a different form.
these things were like the hysteria and the, like,
Mhm.
bubble of insane investment into these crazy, like, fake, in these many times fake companies.
Yeah.
But it's like, well, the internet didn't go away. It became a tool that everybody uses all the time.
Yeah.
Right. And to varying degrees, obviously, the internet's like enormous and all encompassing.
Yeah.
But
But you don't, and you don't have to put on your resume that you know how to use the internet.
you could
You
could
could.
say, I know what the internet is.
But some people do still put, like, I know how to use Microsoft Office.
Yeah,
And it's like, yeah,
that's
we don't
we know.
we don't need to know that anymore.
Yeah, yeah, exactly. That's become a thing that's like, if you don't know how to do that, how are you alive? Like,
Yeah.
so yeah.
But similarly, if people have never used ChatGPT or Gemini or some of these tools to do things, I wonder if that's my wonder. My
Yeah.
wonder is,
Are you going to be screened out
are
if
we
you
going to be
don't?
screened out because you have
Because you
no
don't use it, yeah.
experience using some of those things?
I think it's possible.
It's possible.
I do
I
think it's
don't know.
possible. Yeah.
But yeah, I would be hard. I agree with you. I'm also hard pressed that, like, a hiring manager is like, oh, you're not gonna. Oh, you know what? I think that I think a lot of AI companies are actually pushing the idea that you need to be familiar with our AI tools for getting hired.
Yeah.
That kind of
They're
thing.
like making themselves.
Yeah, they're trying to elevate themselves,
Yeah.
sort of say.
Like, we should push the idea into all research labs
Yeah.
that Pine, if you don't use Pine's rotator and potentiostat,
You'll be a failure.
all your data will be meaningless.
Yeah.
And then someone will come back and say, well, I'm, a zoologist studying pandas. And I'll say, I don't care. You still need Pine electrochemistry products. That panda's not going to rotate itself. You have to buy a rotator. So, these are very important things to learn.
Yeah. Yeah. Sorry, we could probably talk about this ad nauseum, but hopefully that was hopefully it provided a little bit of value to you. That's all.
Yes.
Just something hopefully
Even if it's a little
useful.
silly. Even if it's a little silly.
So we have a question. I actually don't know how best to answer this. It's a very good question. What would be the advantages of using square wave voltammetry to test the sensitivity of microelectrodes compared to CV, cyclic voltammetry?
Yeah, with microelectrodes, it's a good question.
Yeah, I don't know what they look like. I know what the square wave voltammetry looks like on a macroelectrode. I don't know what it looks like.
Yeah, it's a good question. So on a microelectrode, it usually looks like a sigmoid.
Yeah, it normally looks like a sigmoid.
It looks like you've rotated. So what would the square wave signal be for that? And would it matter? I think the only thing that might help. So, like, okay, if I'm thinking about this, and this could be off, right? I guess it depends on exactly what you're studying, but generally speaking, when you're working with a microelectrode, the phenomenon is that like there's no diffusional issues because of how small it is. And so it's like when you do a CV, and you scan negatively or whatever, you get some peak, like that's like CV, right? Whatever.
Yeah.
And then if you rotate or you use a microelectrode, it usually, I'm running out of hand space.
Yeah.
To move my hands. When you do a CV on a microelectrode, you get something like this. It makes like a sigmoid. And so you get this like diffusion limiting current, I sub L, for example. It's a similar thing to what a rotating electrode, right? Because this kind of peak that you get where the current decays is from like a Cottrell, like a response as the diffusion layer grows. And with a microelectrode, there's no diffusion layer, or it's small, or it's fixed. I don't know exactly what is it. How does it work?
It's the diffusion is hemispherical instead of linear.
Oh, okay.
That's kind of.
I thought that there wasn't a diffusion layer, or that it's also fixed, something, or because it's so small, there's no.
So
how does it work?
So
exactly?
It's like the edges. If you think about like
it's like a
the edges of the plane.
Right? It's like a small tip, basically, right? And so the diffusion is like all around kind of a thing, right?
So if you just draw like that's right. So if you drew and if you had like a big circular disc, if you think about the molecules that are diffusing kind of radially on the outside, they make up such a small contribution.
Right.
So on the edges of the glassy carbon, the molecules that come in from that side are very small,
right?
But if the area gets really, really, really small in the microelectrode, they contribute much more,
right? Coming from like all directions,
from all directions. And so I think what ends up happening is, because remember, cyclic voltammograms and stuff like that can all be like simulated based on the nature of like diffusion and solving Fick's law and the Nernst-Planck relationship and linear, differential equations. I don't care.
That's math. Who cares?
It's math. It clears, but it does result in like a different type of signal. It does give you that sigmoid shape.
Right.
So in square wave, you're pulsing the potential, and I
so this is where so we've set that up, right?
So we've set that up.
So what with square wave? So this is CV, right?
Yeah.
So square wave. I'll just start this slide. A little more space. Square wave voltammetry. The waveform, E versus time, is basically this. They're supposed to be even the same, but I can't draw. So, right. So it goes up and then down, and you're taking the difference between this and this. So you're like subtracting the quote unquote background current, basically, right?
Well, I think there's one small caveat, which is I need to let me just double check square wave, because in the waveform, I think the reverse pulse, I think I don't know if it goes down a little bit
it might go
down.
So what you're saying is it might go like this. It's just a matter of where I started, basically, but it started below,
something like that.
I drew the first one down. Yeah, it's probably more like this. So the first, but it's still the same pattern.
You're right. It's still the same pattern.
Yeah.
It's just like the first one. Oh no, actually, when we
I think it can be either. Maybe
it's either.
I don't know. I've seen both drawn, but the point is we're subtracting the forward from the reverse. So what this means, right, is that think about it from a CV perspective, right? If I have current and potential, right? If this is zero current, right? If I have a line for CV, 3 different CVs where at some point it's like this, the square wave. So this is CV1, CV, or LSV, it doesn't matter, right? I'm doing this regular sweep, and I can have different scan rates, so I have different current. Well, the square wave, like here minus here, here minus here, but you can think about it at any point in time, it's all 0. So the square wave for all of these goes to 0. If you have a flat, like CV wave. So to that point, with the microelectrode, if I have something like this, well, here and here will be 0. So the square wave is probably going to be like 0 and then 0. So all you're going to get is a peak where the sigmoid starts or whatever, and then it's going to be back to 0. So the only question is with a sensitivity one, it's possible that like what you're looking for with your microelectrode is this right here, this onset potential, maybe. And it's possible that the square wave will help you clarify the onset potential, because the square wave is looking for the difference. So it's almost like it's kind of like a derivative, but not exactly. But it's like when the square wave really starts to like go negative, that's when there's a big difference between the current and whatever voltage span or potential span you have. And so it's possible that you'll clarify the peak a little better. And it's also possible that the peak position will help you identify the potential that's like let's say the midpoint of my sigmoid. Because at some point this makes a peak because it has to go back to 0 for this section here, right? It goes from 0 to 0. So it has to make a peak, and therefore you're able to get, maybe the E0, if you will, of my sigmoid, of my process on my microelectrode. So that's my best guess. I haven't done square wave on a microelectrode, but just based on how I know a sigmoid works and how square wave works, that's my guess about what you're going to get. So the sensitivity, you might say, for instance, it'll help you maybe clarify the E0 or the peak, or something like peak position. It also might get you to see in some way clarify the onset potential a little bit, maybe. But that's the best that I can answer. It seems logical to me for that. So it was a great question.
Yeah.
Habji has another question. Says, with a pine wafer holder electrode, I connected pin electrode to the top, which has alligator clip at the other end. Can I connect alligator clip to another clip connected by the wire to the potentiostat? Yes, but it's going to add impedance no matter what. So think about it this way. If you have potentiostat cell cable, and it goes to a clip or a post or whatever it does, you want that to be as close to the electrode as possible. Now, that's not always possible. You have to do some connections if you're using a rotator, if you're using a special setup, there's normal things that happen. But one of the things that can make things really tough for data quality is having like an electrode clip to an electrode clip to another wire to a clip to a clip to a thing. Every time you have like a clip connected to another clip or whatever, that introduces a few problems. One is that it adds resistance or impedance to your line, can distort your values. And especially if you're doing impedance experiments, which are very sensitive to resistance, that kind of clip physically can make the impedance measurements either really poor or just difficult. It can mess with it pretty badly. Okay. So one thing is that it might practically mean that your impedance measurements are not really possible, or they'll be very poor quality. The other thing is that you often break the shield. So most cell cables have a shield, like a driven shield around the cables. And often that shield extends just up until the alligator clip because it can't go any further. But it's fine. The alligator will clip to the electrode, and there's a short section of your electrode that's unshielded, but the cell cable itself is largely shielded. Well, if you start adding clips and other kinds of things, you start extending the amount of your system that is unshielded. That can be more susceptible to noise in addition to the added impedance that I just talked about. And it can just make your data noisier. It can make it more, it can pick up other kinds of noise or other kinds of problems. Your data can be of worse quality in some cases for things like that. So the answer is yes, but be aware of these kinds of limitations that can make your data quality a little bit more poor.
We have somewhat limited time.
Yeah.
So I think we might I don't know, maybe we try to talk to, I think, 369 omniverse
So
thing. I think
follow up, I guess.
it's just like a quick follow up,
Mhm.
and that might be the only question we're able to add. So,
Yeah.
Mr. Mursalim, we probably won't be able to get to your question, but please use on our website, go to messages and then submit a question through our website. And next time we have a live stream, we'll be able to answer your question.
Yeah. So
through that way to prioritize your
go ahead
question.
and do it here on our website. There's a little contact up here, and you can submit. If you have an account, you can log in, but you can pick YouTube live stream question submission and type your question in here. We'll get it. We'll be able to save it so we don't lose it. You can put your YouTube handle here if you like. You can attach a file and then type your question from what you've typed now, because we'll be able to get to it when we do our next live stream. Yeah, apologies that we sort of run out of time. As is typical, we made this a half an hour later. We still end up getting questions at the end. It's just how it goes.
Yeah, no, that's all good.
Yeah.
But so this is kind of a follow up on I think you have a wave driver 100, and that's where working and reference are connected together, kind of are connected together, trying to see the current response. Should we run EIS in its working potential mode? So I think that's potentiostatic is what you're referring to.
It's working potential window.
Working potential window. One EIS, and it's so when you do EIS, you're always doing it at a single potential. So it's not like CV where you're scanning within a potential window. EIS is only done at one potential, and we just kind of change the potential. We wiggle the potential with a sine wave within, or galvanostatically, with a current at a specific set point. So there's no like, window, if you will. But one thing I did want to talk about, just because we do have limited time, which is to say that the data points are orange in color, and we have to calibrate the system again to run it normally again after this fault, really. And I'm going to say no. So our data points in our software, depending on the version of Aftermath, first off, they'll almost never be orange.
If there's an overload condition, they will be.
Yeah, if they're only orange if there's a problem, which is if there's an overload condition or for some reason it was unable to actually make a measurement. Sometimes we're able to, if for some reason the potentiostat was not able to make a measurement, instead of like having a blank in the data stream, we put orange dots,
or squares,
or something like that. So that has to do with like maybe a connectivity issue, an overload issue. But if you see orange dots, it usually means, all right, something's a little off, but it does not mean that you have to like recalibrate your entire system. With EIS, you need to calibrate the cell cable, and that's about it. And once it's calibrated, it's pretty good. You don't need to like recalibrate it like every single time you do an experiment. One thing that you can do very easily and quickly is you can run a dummy cell test. So we provide a dummy cell with the WaveDriver 100, or you can use a circuit like a resistor. And if you hook up a resistor, like a 1 kilo ohm resistor, to your potentiostat, and traditionally when we run things in a 2 electrode configuration, the counter and reference are shorted on one side, and the working drive and working sense electrode, which are the orange and red leads, those are connected together, shorted, and connected on the other side. And then you have a reference electrode in between them. You can then run cyclic voltammetry of a resistor, and you should get Ohm's law, basically. Like at every potential, the current value, it's just V equals IR, will match whatever the resistance is. So at 1 volt with a 1 kilo ohm resistor, you'll get like 1 milliamp of current or something like that. So yeah, that's it. Because a lot of the questions and comments have been about kind of weird connections with the cell cable. Like, oh, I have working plus reference connected,
or,
and
or
then
it's working
counter.
with reference and counter. It's hard to tell exactly what
yeah,
the combination is.
Yeah.
And so, yeah, if you have some weird combination that's giving you connection trouble, or giving the potentiostat connection trouble, I guess I'd say,
Yeah.
you might get those orange squares that indicates there's a problem making the measurement, right? So yeah, exactly. Do a dummy cell test, do a resistor test. Like those are ways to make sure the potentiostat is functioning properly. If you do a test on a resistor and you get orange squares, or you don't get anything, or the results don't follow Ohm's law or whatever, well, then there may be a problem with the potentiostat.
Yeah.
But a lot of times it's not. And it's like, there's a problem with the chemistry or the cell or the electrodes of some kind, right? Most often that's the case. It's not impossible for the potentiostat to be damaged in some way, of course, but it's much less likely.
Yeah.
Yeah.
Okay.
EIS is called spectroscopy because spectroscopy refers to light. Light moves in waves. Waves are sinusoidal. Impedance is sinusoidal. Ergo, spectroscopy.
Yeah, it's a frequency.
Yeah, it's a frequency thing. I mean, technically, spectroscopy refers to light, so it's not really, right? But it's like,
yeah.
I mean,
Well,
yeah, we use the term loosely. Spectroscopy refers to like light analysis, if you will, or whatever.
Yeah,
but
yeah. I think any kind of
sinusoidal.
I think anything that's kind of like a frequency
based,
just a frequency basis.
Yeah, that's spectroscopy, and it's
spectroscopy.
electrochemical impedance.
Yeah,
and the impedance is we're perturbing the system spectroscopically, sinusoidally, and it's electrochemical. Hence those three letters. So that's where the letters come from. That's what the words mean.
Yeah.
Marceline, please feel free to use our website if you want to submit some other questions.
Yeah,
but
those questions are a bit.
We're out of time.
More detailed. To answer.
We can definitely try to give a little more thoughtful answer when we have more time. But we have reached the conclusion.
Yes.
And we will not be with you next week, as we said. It'll be a couple weeks, probably back the following week.
Yeah.
Hopefully.
Hopefully.
Anyway, until the next time that we see everybody, I hope that you learn all the tricks that AI has to offer. That's the message I'm going to leave.
That's the message you're going to leave with.
I guess. Okay. Do you have any parting words of wisdom?
No. Just be good to yourself and stay safe. Continue learning. Be patient and
be reckless and impatient and crazy.
Yeah. That's it.
I'm kidding.
Find balance.
Yes, find some balance in your life.
Yeah.
Enjoy things, and we'll see everybody next time.
Yeah.
Bye now.
Bye.